Assalamu alaikum. Today we are starting the second part of our course, that is the reduction of organic compounds. Previously I have just limited my lectures to of oxidation to 12, although we could learn as many as oxidation reactions, but because of taking the account of the time constraints we were restricted to just 12 lectures. So now we'll have to move quickly towards the reduction of organic compounds, and today I'm going to start with the uh, sodium borohydride. We will focus on those reducing agents which are most commonly used in our organic synthesis. So I'm going with a very fundamental reducing agent, that is sodium borohydride. Now, what is the use of this sodium borohydride? Actually, it is a good reducing agent, good selective reducing agent. Why I'm giving a particular emphasis on selective word, that is, this reagent sodium borohydride is particularly used for the reduction of aldehydes and ketones. I am taking a ketone, cyclohexanone. Upon reaction with sodium borohydride in methanol, which is polar protic solvent, upon reduction it changes into cyclohexanol. So why we are calling this reaction as a reduction reaction? You will see that across this carbon double bond oxygen there were no hydrogen atoms, but upon reaction after the reduction you will see that hydrogen has been added. So addition of hydrogen, what do we call? We call it reduction. Similarly, aldehydes. Let's take this. What is the name of this aldehyde? Cyclohexane carboxyldehyde. Sometime in your MCQs, in your entry test, I have seen the questions where they have asked the name of this aldehyde. So you will say cyclohexane carboxyldehyde. So upon reaction with sodium borohydride, most commonly sodium borohydride is soluble in organic solvent, sodium borohydride, especially in the polar protic solvents. So we use the combination of sodium borohydride in methanol in most cases. So after the reaction, what happens? It changes into alcohol. So particularly this reducing agent is used for the reduction of aldehyde or ketone. Sometimes this sodium borohydride can reduce acetyl chloride, or more specifically we'll say in general an acid chloride can also be reduced to alcohols. Now let's talk about the selectivity, and later in the course of today's lecture we will see that why this reagent is very much selective. Let's I'm writing another another compound. Now it has two functionalities, keto group and nitrile groups. So upon reaction with sodium borohydride, nothing is going to happen across this carbon triple bond nitrogen. This functional group remain unreactive. Only the ketone, it is oxidized to alcohol. let's let's take another example. What is the name of this compound? Ethyl acetoacetate. Sometimes we called it EAA, ethyl acetoacetate. Upon reaction with sodium borohydride, what happens that this functionality, the ester, it does not react. Only the keto group reacts and undergoes reduction to alcohol. So what I'm talking about, I want to convey you that this sodium borohydride reducing agent is used select for the selective reduction of ketones, aldehydes and acid chloride. Now let's see that how this reduction actually occurs. We will first discuss the structure of sodium borohydride. That is very important and it will answer us many questions. What is the structure of this BH3? This is a type of AB3 molecule, AB3 type molecule. And what is the hybridization in AB3 molecule? We know that sp2 hybridization is there. But in case of BH4 ion, it becomes AB4 type. And what will be the structure of this? It is trigonal, planar, and it has a structure of tetrahedral structure. What is the electronic configuration of boron? Boron has atomic number 5, so 1s2, 2s2, 2p, 1. We'll focus on the valence shell. And for the hybridization of sp2, one of the electron shifts or promoted to this empty 2p y orbital. Then these three orbitals 2s, 2px and 2py, they undergoes hybridization and they become degenerated hybridized orbital. So because they are single electrons, we can write like this. And 2pz orbital, it remains unhybridized. So across this boron, These three sp2 hybridized orbital, they will remain oriented like this, and this 2pz orbital, remember it is empty orbital, 2pz, it has not any electron in it. This unhybridized 2pz orbital, it serves as an empty pocket. These three sp2 hybridized orbitals, they overlap with 1s orbital of hydrogen, 1s, 1s. These three hybridized orbitals make overlapping with 1s orbital of the hydrogen. So this is a structure of boron trihydride. Boron hydride, simply we call it boron hydride. So you will see that three hydrogen atoms occupy the corner of a triangle, and 2pz orbital, which is empty orbital, it can accommodate a pair of electrons. So BH3 has a deficiency of two electrons or a pair of electrons. So that is why they are called Lewis acid. What are the Lewis acid? Those compounds that can accept a pair of electrons in them because of the presence of the empty pocket of the orbital, unhybridized orbital. Those are called Lewis acid. So what happens when hydridine, it has a pair of electron that can be donated to a Lewis acid. So what will happen when boron hydride reacts with hydridine? We get boron hydride. And what is the structure of this boron hydride? You will see it has tetrahedral structure, as I have told earlier that it belongs to the class of molecule that has geometry of AB4 molecule. Hydrogen, hydrogen, no, four hydrogen are now occupying the corners of the regular tetrahedron, and this boron, it has negative charge. The pair of electron has been donated to the 2pz orbital of the boron unhybridized, and because hydride is added in the form of sodium hydride, so the sodium ion makes the electrostatic force of attraction. So this is the structure of sodium borohydride. We simply write it NaBH4, but it is actually like this. You will have to imagine sodium borohydride always in your mind like this. And this sodium borohydride is a good source of hydride ion. This boron, it is negatively charged. It will definitely would like to give the pair of electron to someone. So it can, this hydride ion, can be donated to other compounds. So let's now look at the mechanism of the reduction of ketone using sodium borohydride mechanism. Here I want to tell you that this sodium borohydride is also water soluble. Also, it is soluble to highly polar solvent like methanol, ethanol, DMF, etc. So, solvents can be classified into two types. All these four solvents are polar solvents. And if the solvent has active hydrogen, acidic hydrogen, then those solvents are called polar protic solvent, like water, methanol, ethanol, etc. Or in these three solvents, you can see that hydrogen is attached to the highly electronegative element, and so this hydrogen is acidic. So we call these solvents as polar protic solvent. Now, what about this DMF? This is NN dimethyl formamide. NN dimethyl formamide. It is polar solvent, but this is called polar aprotic solvent because hydrogen is not attached to the highly electronegative element, so no acidic hydrogen is present, although the solvent is very much polar, but this is called polar aprotic solvent. This sodium borohydride is soluble in polar protic as well as polar aprotic solvent. So there are two mechanisms. When sodium borohydride is dissolved, in most of the cases, in most of reactions, you will see that we will use methanol. So this is polar protic solvent. And what is the mechanism? I think I should move to another next page for the better understanding. Let's take a journal ketone mechanism. R and R may be same or different. R1 may be hydrogen, R1 may be, what could be R1? R1 may be alkyl, aryl, halide, or hydrogen. And what happens? Sodium, I'm going to write now the structure of sodium borohydride. You should always write the structure of sodium borohydride like this. You should practice. So this is, here we have a boron, negatively charged boron, and sodium ion is around. So sodium borohydride. So what happens? This sodium borohydride, it is a source of hydroid ion, and this keto group, it is polar group. We know that carbon bears partial positive charge while the oxygen carries partial negative charge. So this is a polar functionality. So what happens? This boron donates the hydride ion to this electrophilic center, electrophilic carbon. it needs a pair of electrons, and borohydride is a good source of hydride ion. So what happens that hydride along with its pair of electrons, it acts as a nucleophile. Hydride ion, it's electron rich, it needs a nucleophile. So it attacks on this sp2 hybridized electron deficient, slightly electron deficient carbon, and this pair of electron moves over the oxygen. So what you get, negative charge over here, and hydride ion. Now this is very important that this hydride ion can attack from the backside, or this hydride ion could attack from the front side, negative charge. And someone has to balance this negative charge, since we have sodium. So sodium balances this negative charge, and we get BH3. What happens next? In the next, since we have polar protic solvent, that is methanol, this oxygen, it abstracts the hydrogen from methanol, so you get hydrogen. You can see it, it plucks this hydrogen, so we get an alcohol, or you may also have alcohol like this. If the R and R1 are different, then definitely you will get two stereoisomers, and they will be enantiomers. If these R and R1 are different, then you will get a pair of enantiomers. And since this hydride ion, which is a very much smaller, it has equal probability of attacking from backside or from the front side. This keto group, it has a planar geometry. So planar, it's the same like we have already drawn on the page. So hydride ion could attack from the front side while approaching this electron deficient carbon, or it can attack from the back side. So that is why we are getting two different stereoisomers. This is a mechanism when you will use polar protic solvent. Now let's discuss the mechanism when you will use polar aprotic solvent. Mechanism. Let's take a simple ketone that is known as acetone, and we are simply using boron trihydride in aprotic solvent, sodium borohydride, sorry, anyway, in DMF or DCM. So these two are polar but aprotic solvent. They cannot donate the active hydrogen or the acidic hydrogen whenever needed. But in such mechanism, the final workup is that you will have to perform hydrolysis in the next step, in the final step. Now look, the mechanism, This uh, I should draw like this for your better understanding. We have four hydrogen attached to this boron. In the same way, it's a good hydridine donor. Hydridine acts as a nucleophile. It attacks here, and the negative charge, oxygen gets negative charge because of the moving, because of the pair of electron density that now resides on this oxygen. So you will get hydrogen here, oxygen will get negative charge, and BH3. Now what happens that this negative charge, because we don't have a polar product solvent where this oxide could abstract the hydrogen from that one, so it donates this electron density to boron, because boron has an empty pocket of 2p orbital. It can accept a pair of electrons. It's a Lewis acid. So what happens, you get this. I'm not showing hydrogen here now. B hydrogens, and this is getting negative charge. This hydride, boron trihydride, now it has three hydridine that can be donated to ketones, ketone molecules, one by one. So in the next step, another molecule of ketone, it has negative charge. This hydridine acts as a nucleophile. Oxygen gets negative charge that can be donated to boron. So you will get this species. Still, it has two hydridine. So now I am after two more attacks of this hydridine to another molecules of the ketone. Finally, you will get this species. And this oxygen will get negative charge, and sodium ion will surround this species. So because you are not employing any polar product solvent, so the reagent would react, and 1 mole of this sodium borohydride would react with 4 moles of ketone. Now what happens in the final step, that I have already told you, that after the reaction you will have to perform the hydrolysis. Now hydrolysis, acidic hydrolysis takes place. How? The bond breaks from here, and OH attacks here, hydrogen attacks here, and similarly on the other side as well. So finally you get 4 molecules of alcohol and BOH 4 molecules of this boron hydroxide ion, and later sodium is around. So in this way you will get four molecules of the alcohols. Oh, I hope you would have understood this. The question arises that why this sodium borohydride is very selective. So we will study four important reducing agents. The first one is lithium aluminum hydride, lithium borohydride, sodium borohydride, and sodium cyanoborohydride. These are two very important reducing agents, and their order of their reactivity is like this. Lithium aluminum hydride is a most powerful reducing agent. It reduces almost every class of the organic compound. It reduces nitro group, reduces esters, amides, imides, sulfonic acids, carboxylic acids, uh, alkynes, and many others. So this is very much powerful oxidizing agent. Then comes the lithium borohydride. Then comes the sodium borohydride. So this is a relatively less reactive reducing agent. Why? So remember, whenever here lithium is attached and here the sodium is attached, the lithium is has a greater charge density as compared to sodium ion. So smaller ion having positive charge attached to hydride ion donor are the powerful nucleophile, are powerful reducing agents. Here sodium has less electron density as compared to lithium, so they are less uh, reducing agent, less reactive reducing agents. Now we compare these two. Sodium borohydride has a structure like this, negative charge, and this sodium cyanoborohydrine, it has structure like this. Both of them have sodium ion electrostatically attached. Now what happens, why it is a good hydride donor and it is not, that this negative charge can be delocalized. So boron becomes like this. This boron cannot donate the hydride ion to other molecule because it is not electron rich now, because the negative charge of this boron is now can could delocalize over this nitrile group. But here in the sodium borohydride, it can donate these four hydride ions, so it is comparatively good reducing agents. So what are the reducing agents? Those compounds that can donate, that can give the hydride ions to other molecules. So it can easily give off these hydrogen ions, but it cannot. So it's a good reducing agents. Now why it is selective? What compounds could be reduced using sodium borohydrides? Remember, aldehydes, ketones, imines, acid halide, and imides. what do you call these compounds having these functional groups are called imides. Acid halide and especially acid chloride, imine, aldehyde, and ketones. Sometimes ozonides, ozonides. Do you remember these ozonides? When alkene reacts with ozone, then ozonide is formed. So ozonide can also be reduced these sodium borohydrides. You can reduce 1, 2, 3, 4, 5, 6, 7 class of the organic compound using sodium borohydride. Now, what functionalities cannot be reduced using the sodium borohydride? You cannot reduce ester, you cannot reduce nitrile, you cannot reduce epoxide, nitro, alkene, alkynes, amides, and many others. Now let's look some of the examples where the sodium borohydride has been employed. I will solve some of these problems for you, so remaining you will have to solve it by yourself. Let's first discuss this problem A. This is a compound. What is the name of this compound? It's a ester. Ethyl 1 2 3 4 5 5 oxo ethyl 5 oxo 1 2 3 4 5 6 hexanoate. Now upon reduction, what will happen? This functionality will remain unreacted. Sodium borohydride cannot reduce this ester. It will reduce into this ketone, and the final product will be alcohol. Here you have two keto groups, both will be reduced. Another very famous aldehyde, this is called cinnamaldehyde. Sodium borohydride cannot reduce this alkene or benzene, so only aldehyde will reduce and you will get the alcohol. This problem you will solve, but I think I should explain more for these problems. This is example of imide. Sodium borohydride can also reduce imides. How? Let's check it. Reduction of imide. Reduction of imides. Let's take an imide. Sodium borohydride. Can I draw sodium borohydride like this? Yes, I can draw. It is a hydridine donor. It will attack here, and this oxygen moves. Oxygen gets negative charge. What happens next when this negative charge comes back? This bond ruptures and this pair of electron bond pairs moves on nitrogen, so you get since we are using methanol, so this nitrogen will abstract hydrogen from this solvent. So you can say that MEO negative it leaves, and this hydrogen is plucked by this amide. So your active species becomes this one. And we know that the sodium borohydride rapidly attacks this aldehyde and converts it into ketone upon reduction, while other functionalities, the olefinic as well as amide, they remain unreactive. So this is your final product. You will have to solve this problem by yourself. What is the name of this compound? This is called Thalimide. So upon reduction with sodium borohydride in product polar solvent, what will be the answer? You will have to solve it by yourself. Now, in lecture I have told you that sodium borohydride also reduces the ozonide. How this reduction occurs? Reduction with ozonide. We know that when alkene react with ozone, you get this ozonide. I'm not going to explain you the mechanism, because in oxidation reactions I have explained that how this ozonide is formed. And when this ozonide is formed, when it reacts with sodium borohydride in methanol, what happens that you know that you will get two molecules of the aldehydes, and these aldehyde can easily be reduced using this sodium borohydride. So your final product will be 2 moles of these alcohols. So in your exam, when someone asks you to convert this alkene into this alcohol, so you will have to remember that first you will have to perform the ozonolysis. Cleavage will occur across this double bond, and you will, after reduction with sodium borohydride in methanol, you will reach to this alcohol. Also, this sodium borohydride can also reduce imines, carbon double bond nitrogen. What we call it, imine, is the same like aldehyde or ketone. In ketone you have carbon double bond oxygen, but in imines you have carbon double bond nitrogen. Upon oxidation with sodium borohydride, hydride ion attacks here as a nucleophile. This charge moves on nitrogen. Nitrogen gets negative charge, and since you are using polar protic solvent, this amide nitrogen, negatively charged nitrogen, it will abstract the hydrogen from the solvent, and your final product will be this one, amines. So sodium borohydride can reduce imines to amines as well. So now let's conclude today's lecture, that is the use of sodium borohydride as a good selective reducing agent for aldehyde ketones, acid halides, as well as imines, ozonide, etc. It cannot oxidize, it cannot reduce. Sorry, I'm while giving you the lectures of the oxidation, the word oxidation has now stick to my mouth. So uh, now we'll have to focus on the reductions. So while the reducing the others, this sodium borohydrides is not as good reducing agent. It cannot reduce esters, nitro compounds, sulfonic acids, amides, um, epoxides. All these other species remain unreactive. So remaining these two problems, G, H, I and J, these four problems you will have to solve it by yourself, and after solving show me so that I could check. Thank you so much.